We're about ready to resume our discussion of software architecture. Does anyone have any questions that they came up with after our discussion last Tuesday or Monday? Okay, let's go ahead and get started then. We're going to talk about some more issues associated with architecture. In particular, we'll talk about documenting architectures. We'll talk about the position of architecture in the modern world, especially as seen through the lens of agile methods. The agile methods are frequently characterized as paying little attention to design. And I would actually disagree with the argument that agile methods have deprecated design. Design is still important in the agile world. It's design documentation that has been deprecated. There is an emphasis on UML as sketch. In the agile world, you do the design as an activity. Your design may be documented on a whiteboard, and then you write the code, and then you erase the whiteboard. But that doesn't mean that agile teams do not concern themselves with design, that they don't spend time doing design. They just don't argue that design documentation is necessarily something that you should keep around. If you're not going to maintain the design documentation, then there's little point in doing that. So we'll talk a little bit about the agile perspective on design and on architecture. And we'll talk a little bit about the value that we can get from maintaining architectural level documentation. We're also going to talk about some of the trade-offs that we make in coming up with our architectural design, and discuss just a little bit some of the issues about the future of architecture and design in general. We're going to start off with a discussion of documenting an architecture. This example is called Adventure Builder. It is from the book Documenting Software Architectures, and there are several different views that are contained in this particular example. You can go to the SEI website to take a look at this, or you can buy the Documenting Software Architectures book if you wish to. Adventure Builder is basically a travel company. It's very similar to Travelocity or any of the other travel sites that are out there. The idea is that we will build adventure packages for vacationers. This was originally developed at Sun as an example, and there was a book that was written on this back in 2004 by Singh that talks about this particular design, but the source code and the documentations for this particular case study are available for download if you're interested in taking a closer look at it. There are several use cases that are associated with the Adventure Builder website. First off, the user can visit the website and browse the travel packages that are available. And they include making travel arrangements, so that you can fly to wherever you're having your adventure vacation, lodging options in terms of hotels, B&Bs, cabins, whatever, and then whatever activities that you might be interested in participating in, which includes things like mountain biking and fishing and going surfing and scuba diving and things like that. So you can pick the transportation and the level of accommodation and the different activities that you want to engage in and basically tailor your own vacation on this website. So one of the use cases is going to be to place an order. And when you place an order, the system is going to have to interact with a number of different entities. There will be a bank. You're presumably going to be paying by credit card or perhaps debit card. You'll be making flight arrangements. You'll be making hotel arrangements. You'll be booking the various activities that you are interested in participating in. The user may want to come back and check on the status of their order because some of these bookings may take time to complete. There's a diverse set of companies that are going to be engaged with on this system. And some of them may have limited resources, and it may take hours or even days to complete and confirm a booking with some of these companies. So the system is going to have to interact with the airlines and the hotels and the activity providers to make sure that we have the most recent offerings available in the catalog on the website. So that's another kind of interaction that's going to occur. And so here is our set of use cases. A vacationer may want to browse the catalog and order travel packages and track their order, and then the various other vendors out there, the bank, the airlines, the lodging providers, and activity providers are all going to be interacting with providing the travel packages and paying for them. The activity providers and the lodging and the airlines are going to have to update the catalog. The vacationer will be looking at tracking their order, but won't be necessarily interacting directly with any of these other external actors. This is a use case diagram here, or more properly, what I would call a use case context diagram, because it describes all of the different use cases. We have 4 use cases listed in this particular picture, which are part of the Adventure Builder system. A use case context diagram treats the system, the Adventure Builder in this particular case, as largely a black box, which interacts with external actors such as the vacationer, the bank, and so forth. Now, what are the quality attributes that are going to be applicable to these various web services? Well, one of the quality attributes is modifiability. And so if we have new business partners coming in that want to add their particular services to the Adventure Builder, the requirement here, the modifiability requirement is that you should be able to do that in 10 person days of effort or less. So here, the objective is easy modifiability, easy change to integrate with new business partners. You don't want to make this an onerous exercise. So that's a pretty realistic modifiability requirement to establish. Performance requirement. If somebody places an order, you would like for the user to be able to see that the order has been successfully submitted within 5 seconds. Now, being successfully submitted is not the same thing as confirming that all of the adventures have been booked, because some of those may take hours or days. But the user can be confident that their order is in the system, and they can check on the status of it for any that may take longer to get a confirmation in. We would like for the system to support 500 simultaneous users in terms of normal operation. The assumption is that those 500 users would follow a random distribution over a period of a minute under normal operating conditions. And you would want your maximum latency to load your first page be under 5 seconds and average latency to be less than 2 seconds. So again, this is a pretty reasonable performance requirement. Average latency of less than 2 seconds is perhaps a little bit aggressive, depends upon the amount of business that you have to deal with. 500 users is not an enormous number of simultaneous users to be supporting at the same time. So it seems like 2 seconds is probably a reasonable target latency. In terms of reliability, what if your order processing center gets a request but does not reply to the consumer within 5 seconds? So that was our maximum waiting time. Well, if we don't get that reply back, then the consumer website will resend the request. And that means that we've got potentially a duplicate request going in to the order processing center. So if the order processing center gets a duplicate request, you want to make sure that the customer is not charged twice. We want to make sure that our data remains in a consistent state. So if we, bounce on the submit button 5 or 6 times, that should just be one, treated as one submission. And then if the request is successful, you want to make sure that that is acknowledged 100% of the time. In terms of security, we're processing credit cards. That's obviously something where we want to make sure that we have security, so confidentiality and integrity are going to be important issues there. We also want to make sure that transactions cannot be repudiated. That is a security attribute that I kind of mentioned in passing. Non-repudiation basically means neither party can come back later and say, no, I did not agree to that. There's got to be closure, or responsibility, accountability held for the orders that are being made. So this will make sure that we meet our obligations in terms of secure transactions. If there is some kind of denial of service attack, then we want to make sure that we detect that there is a problem and we notify the system administrator, and we continue to operate as best we can in a degraded mode. You want the system to be available 24/7. If there is a time when the order processing center fails, you want to notify the system administrator within 30 seconds. Continue taking orders until you can reinstantiate the order processing center. Make sure that the data remains in a consistent state. So you need to basically design in some fault tolerance into the software here. Now, before we continue on with this discussion, in thinking about this particular case study, do all of these quality attributes seem reasonable to you? Are there any that perhaps you would not have thought of immediately if you were designing the system? Does having a checklist of common quality attributes like availability and interoperability and modifiability and performance and security and testability and usability, does having that set of common quality attributes inspire you in eliciting requirements? Would you have thought about the modifiability quality attribute that we can update the website with a new partner in less than 10 person days of effort? Is that something you would have necessarily thought of? Would that have affected the way that you designed the system? If you think of it or don't think of it, is that going to affect the way that you go about doing things? No, those are all, I think, legitimate questions to consider. And I will freely admit that being a regular human being, there are things that I would overlook if I did not have checklists such as this that could inspire me to think about, what are the availability requirements? What are the modifiability requirements for this particular system? Having those checklists as a thing to inspire discussions with the different stakeholders and make sure that we do a reasonably good job of covering the waterfront there is, I think, probably a pretty useful thing. Next thing we're going to talk about is some of the different views that are out there. We've got a template that we're going to use here. We're going to start off with our primary presentation of what the architecture looks like. We're going to talk about the element catalog, a context diagram, a variability guide, design rationale document, and discuss any related views. Let me just say right here, when we're presenting the graphics for our architectural design, one of the things that you have to ask yourself is, who's the audience? Who's going to be seeing these pictures? What is their interest going to be? You will pick the views that capture the issues that are of concern to the different stakeholders who are important to your particular community. There's lots and lots of different views that you could have into the system. Not all of them are going to be important to every stakeholder. And so you have to decide which views and which notations are going to be relevant and informative to different audience members that you may have. So in this particular case, we've got a module uses view here. So you can see here that we've got the consumer website and the order processing center. There are a couple of applications out here. The order processing center is interacting with the bank and the airline and the hotels and the activity booking centers. It's interacting with the consumer website, which has various protocols that it is using to capture information, audit trail information, things like that. The consumer website is going to let the user browse through the catalog and place orders and track the status of orders and create purchase orders and pass them on to the order processing center. This is actually going to be an implementation of the model view controller. This is a big, web sites are frequently, heavily graphical in nature. And so in this case, we'll use a variant of the model view controller called WAF, the Web Application Framework, which is implemented using entity beans. And so we'll have a bunch of apps out there, servlets and things that implement the WAF framework. And we'll also got another framework called GWT, which we'll use for the client, or at least part of the client-facing code in there. And that's captured on that diagram that we have on the previous page. Now, you may or may not know what GWT and WAF are. Are you a Beans user, or do you do JSPs and things like that? Different people will be familiar with different applications. You may or may not be familiar with those specific technologies, but you have a kind of an idea when you say that this is a model view controller pattern. And so the WAF is a variant of the model view controller pattern that we're talking about there. The order processing center is where we implement the business logic for the system for accepting purchase orders and checking on the status of purchase orders and communicating with the external suppliers and communicating with the customer about what's going on with the application. Here's a module decomposition view. This is looking specifically at the order processing center. And so you can see here some stuff with enterprise Java beans and workflow managers and purchase orders and web service brokers and things like that that are going to be. So this is a package diagram that shows what the order processing center pieces are going to look like. In this particular case, enterprise Java beans was picked primarily because the developers were already familiar with enterprise Java beans. And that's sometimes called the availability heuristic. We use the techniques that are available to us in solving the problems that we run into. Is that necessarily the best solution? You could debate that all day, but is this a satisfactory solution is probably a more useful question to ask. And in this particular case, you can certainly argue that that's a reasonable solution to try using. Here is another view in here. This is for the order processing center again. This is a module uses view. In this particular case, here's the workflow manager in the center of everything, talking to various packages out there, financial services and invoice services and order fillers and things like that. And then some of those in turn are communicating with external actors such as the bank and the airlines and the hotels and the activity booking centers. Now notice that we're using UML package diagrams here. So that's the particular notation that we're using in this picture. So if you know the UML notation, there's 14 different kinds of diagrams that are used in UML version 2, I should say. There are 7 static views. There are 7 behavioral views. And so here we're looking at one of the structural views, one of the static views, which in this case happens to be package diagrams. Here's a little bit of a picture of the workflow manager. So you can see the workflow manager in there is talking to the purchase order handler and the invoice handler. You got a package which contains those particular elements of the system. And those may be talking to various and sundry other things out here, such as the order filler, the order receiver, the process manager, and so forth. We might create a data model. Here we've got a data model of the different kinds of data that's moving back and forth on the system. You've got a purchase order, which is kind of the center thing here. This is using not UML, but an information engineering kind of notation, where we've got data that is communicating with various or related to various and sundry other data. So the lodging is going to be related to the lodging order, which is going to be related to the purchase order, and so forth. So depending upon whether or not you're familiar with information engineering, you may or may not be happy to use this particular notation in doing your data modeling. Here is another kind of modeling. This is an SOA kind of view. Note this is called an informal notation. This one is a component and connector kind of a view. This informal notation is one that was popular back in the 60s and 70s. You'll see that we've got databases which are represented basically by disk drives. That circular thing there used to be a disk drive, and now we use that to represent databases, or perhaps more correctly, data repositories. We've got web service endpoints notations in there with the arrows going back and forth to those. We've got our client-side applications in terms of the web browser and the email client. We've got some Java applications in there. We've got some external service providers in there. And so you can see how each one of these is connecting together. We've got some ports that we're using to connect the different pieces of the system together. And you can see that the Adventure Builder is in a box all by itself here with the dashed lines around it. And then other things outside. Notice the web browser is inside the Adventure Builder box. Here is a similar picture in a UML kind of notation. So this is a component diagram. So if you're familiar with component diagrams, you can see that we've got the lollipop notation for connecting the different components that make up the system here. We can use this as a way of capturing a top level picture of the service-oriented architecture that we have for the system that we are designing. This is a similar notation for that, which is based upon a notation that's generated by an organization called SOA Patterns. So you can go to the SOA Patterns website and see their particular notation, which they argue is a good notation to use in describing service-oriented architectures. This is one of the things that we simply, just a reality of the modern society. There's bunches of different notations, bunches of different standards out there. Some of them you may find useful. If so, feel free to take advantage of them. This is a notation that people doing service-oriented architectures might find useful. UML is a very well-known, widely used, standardized notation. And you can certainly use UML to describe the architecture for many systems. But UML is really arguably best suited for mid-level to detailed level kinds of designs. When you get into more abstract things, it doesn't have quite the power of some of the other notations, or at least arguably doesn't have the power of some of the other notations that are out there. And so you may pick up one of those. I have a friend who really likes mind mapping, and uses that to take notes in meetings. It's a very flexible graphical kind of notation. So if you're familiar with mind mapping, you might find that a powerful notation that you would like to use. Personally, I'm graphically challenged, so I don't do things like that very much. Here is one. This is a little bit more of the informal notation kind of view. This is a multi-tier kind of a perspective. So remember the multi-tier architectural design pattern. What we have here is breaking the system up into client, web, enterprise Java beans, and backend tiers. And you can see here the different pieces that have been assigned to the different tiers here. So you can look at the different pieces. There's a key down at the bottom that explains what the different boxes and lines mean. So a dashed line with a stick arrowhead is a Java call, and a dotted line with a triangle head is file IO, and so forth. And so again, this is the semi-formal notations are not quite as standardized as UML and perhaps the SOA patterns notation might be. Let's see, here's another component diagram view, UML view. This is for our order processing center again. Again, what are the things that you want to highlight in your particular picture? It seems like in this particular case, we're interested in looking at the different components that make up the order processing center, and we want to look at the communications between them. This is component and connector view again. Again, we're using the lollipop kind of notation to indicate the communication that's going on between the different components that make up these particular systems. And you can see down here that we've got some stereotypes, MDB for a message-driven bean, SLSB for a statless, is that supposed to be stateless session bean? Entity beans, JMS for a connector that uses a JMS queue. So if you're familiar with those particular technologies, then you can look at this particular picture and have a pretty good idea of what's going on in this particular application of our overall system that we're designing. Here is a deployment view. So we're looking at how we're going to allocate things. This is an informal notation. So you see a firewall there kind of in the center, which is represented by a brick wall across the connector between the Adventure Builder local network and the internet. So that gives you an idea that we've got a firewall between us and the outside world. The outside world is where the internet is where the banks and the airlines and the hotels and the activity providers are going to be doing their stuff, and where our customers are going to be, running their web browsers. And so everybody's going to be going through a firewall that will hopefully protect us from some of the security attacks that might occur here. And so here we have something called Glassfish. So we've got some instances of that in here on our server machines. And then we've got various data stores like the Adventure Catalog database and the Order Processing Center database and the service registry and things like that. And those are all interconnected together with the local network, which is behind the firewall for our particular system. Here's the deployment view from a UML perspective. And just think about, these different perspectives. This one, this one, this one, this one. They're basically saying pretty much the same thing here, right? Perhaps some different levels of detail. Now, do you like this kind of informal notation? One thing that's explicit here that is at best implicit on this other diagram is the firewall. Is SOAP providing the firewall that's separating these things? That's not really good, but what would you're maybe not capturing all of the same information on both of these charts, even though in principle they are pictures or very similar pictures of the same thing. But it is an interesting thing to take a look at, isn't it? Here's our install view. This is another allocation view. So here we're looking at installing stuff on different nodes in the system that we might be concerned with. So we're allocating the different applications to different components of the system that we're going to be acquiring. And so that just gives you a very high level, 50,000 foot overview level of some of the notations that are out there. And I did not really talk about how you come up with those designs, or I use that notation. And it may or may not have been obvious to you what the different graphics there were capturing about the design. A lot of times we had different pictures that were showing very similar views for some of the different things in there, just to illustrate some of the different notations that are out there. The whole point of that is that when you're documenting the software architecture, there's lots of notations that you can use. UML is very popular. I certainly would not want to discourage you from using UML, but do be aware that for architectural level documentation, UML tends not to be as strong a support. And you can draw your own conclusions about whether UML is well suited for capturing architectural level notations or not. Now I want to switch over a little bit to talk about another one of the issues that we were discussing earlier, which is the use of architecture and agile methods. And I think it's fair to ask, what is an agile method? Most undergraduate students do not know what agile is. If you've been in any of my courses, there's a pretty good chance that you've seen a lecture on agile methods. I tend to talk about in most of my courses, I tend to mention agile because agile is very popular in the software world today. But there is not a good short definition of what agile is. We call agile methods agile because in 2001, a group of methodologists got together in Snowbird, Utah, and talked about what the commonalities in their different lightweight methodologies were. And they did not like the term lightweight for fairly obvious reasons. And so they said there's a lot of stuff that we agree on, and we're dealing with a lot of the same issues. And so we're going to call the category of methods that we are all independently developing the agile methods. And one of the things that they all share is that they are designed for dealing with environments that have highly volatile requirements. And so a definition that I frequently use is that an agile method is one that supports responding rapidly to changing requirements. Now, when you look at the Agile Manifesto that those people came up with in Snowbird, Utah, it's a very short set of 4 values. There are also 12 principles that were stated by the people and everybody signed up for. Which are principles that they all pretty much held in common. But they said there's a general agreement within the Agile community that we are not really building methodologies. They do not want to describe any of their methods as being methodologies. Ken Schwaber says that Scrum is not a methodology, it is a philosophy of design. And one of the big drivers for that is an explicit recognition that you have to tailor the Agile method for the specific needs of the context that you're doing your project in. No, the problem with that is that it gets really slippery to say what is or is not required for a method to be a faithful rendition of Scrum or extreme programming or any of the other methods that are widely accepted as being agile. So for example, do you have to be doing some kind of iterative development in order to be considered an agile method or an agile team? And I think there would be pretty much universal agreement that you have to be doing iterative development in order to be considered agile. Now, what we might get into an argument about is how long can an iteration be? Back in the early days of the Agile movement, some of the methodologists were saying that an iteration could be 2 or 3 months. In the Agile principles, it says from a couple of weeks up to a couple of months. I think today that the most agile methodologists would get very nervous when you started getting an iteration up to say 6 weeks. The most popular iteration length today is 2 weeks. Scrum, when it started out with a 1 month iteration length. And now pretty much all of the literature about Scrum talks about 2-week-long iterations. So relatively short iterations were intended from the beginning. That's actually in one of the Agile principles. But they don't say exactly how long an iteration should be. But there would be qualms if you had one that was 2 or 3 months long, certainly these days. Although in the 1990s, that might have been considered acceptable. Secondly, a lot of the Agile principles and some of the Agile values talk about the developers, the empowerment and participation of the developers, that the developers are proactive members of the team. To what degree is that required in order to be agile? And I think that you will get into some interesting arguments about that particular point. Philosophically speaking, if the developers aren't part of a self-organizing work team, it's difficult to believe that you could really implement an agile method in the spirit of agility. I'm certainly not going to say that it could not be done, but I am going to say that it is difficult for me to see how that could possibly work. You would violate the spirit of agile if you don't have an empowered development team. So, that may not be an absolute requirement, but it's hard to see how you could successfully do agile without that one. Do you actively collaborate with the customer? Interacting with the customer on a daily basis is part of agile. It's one of the values that's embedded in a couple of the principles. Do you need to be actively collaborating with the customer? And the problem there is the customer may not want to collaborate with you. What the customer say is, I've told you what the requirements are, go away and quit bothering me. Can you still do agile in that kind of environment? And there are things that you can do to create a customer surrogate to play the role of the customer for an agile team. But you have to recognize that those kinds of surrogates are not going to be as effective as having the active collaboration of the real customer and the real stakeholders. But that's a real world issue that does pop up. And all of these impact the architecture of the system. If we are doing iterative development, when do you develop the architecture of the system? If those are the critical early design decisions, do you take time at the beginning of the project to come up with the architecture? Are you going to wind up with saying, okay, we're going to have some architectural iterations in here, and then maybe we'll have some design iterations, and maybe some implementation iterations, and maybe some testing iterations? No, that's an absolute violation of the agile philosophy there. So architecture is going to have to fit into an iterative life cycle in a way that does not dominate the early iterations. Empowerment of the developers, yeah, that can still take place. The customer frequently is the source of the architecturally significant requirements. So the quality attributes, as we'll talk about in just a little bit, that drive the architecture. And so active collaboration with the customer is certainly going to be a positive thing in coming up with the architecture. I mentioned the Agile Manifesto. This is it. Along with the participants in the Snowbird meeting, we're uncovering better ways of developing software by doing it and helping others do it. We have come to value individuals and interactions over processes and tools. What does individuals and interactions mean? Individuals and interactions means that we value people who are working together as members of an effective team over defining processes and tools. Now, there is value in processes and tools. That last line down there, while there's value in the items on the right, we value the items on the left more. Do you value competent people working together as part of a real team over processes and tools? Now, I spent 25 years of my career working in the software process world. That's the thing that I'm known for. I absolutely agree with this valuation. I said 30-something years ago that the best process in the world will not help you if you don't have good people on your team. So, a good process will enable competent people to work together more effectively and efficiently. And if you have a bad process, that will be a barrier that prevents or hinders people from working together effectively. So there is value in process. And I can talk all day to you about software process, but I will tell you right now that the people, competent people, working together as members of a real team is much more important than processes. People working in teams are much more important than tools. Now, you have to have tools to do the job. If you don't have a compiler, you're up the creek as far as building software is concerned, aren't you? You've got to have an IDE, you've got to have editors, and you've got to have compilers and linkers and all of that kind of good stuff. You need automated configuration management tools. You need automated testing tools. That is certainly critical for being able to work on a project in today's world. No question of that whatsoever. But the best tool in the world is not going to build good software if you don't have competent people working as part of a real team and doing the job. So I don't know many people who will argue about the truth of this first statement. The second statement here, working software over comprehensive documentation. It's kind of hard to argue with that. The objective of building code is to build a program that works. The documentation is certainly should be playing second fiddle to that. The probably the critical point there is that idea of comprehensive documentation. The heavyweight methodologies that were being implemented in the 70s and 80s that the agile guys were reacting to in the 90s were creating overwhelming amounts of documentation. Capers-Jones reported that on DoD projects, there was 4 pages of documentation for every line of ADA code in some of the projects that he was looking at. 4 pages of documentation for every line of code is excessive. Where do you draw the line? There was an awful lot of detailed design documentation that was generated on projects in the 70s and 80s that we knew did not add value. If you were working on maintenance on a software project, certainly in the 70s and 80s, when I got started in the software industry, I can remember looking at a C5 spec, which was a detailed design description of a system, and then looking at the code, and the detailed design did not match what the code actually did. And I was very young at the time, and I was a little bit surprised by that, but it was clear that the design had not been maintained in parallel with the code. So as things change, and things always change in the software world, once the design is signed off on, we typically do not go back and maintain the design documentation. Sometimes we don't even maintain the requirement specification, which is a little bit more problematic. You can argue about whether or not architectural level documentation is easy enough to maintain that you should be willing to invest in maintaining that documentation because of the value that you get out of it. I think I've got some slides a little bit later talking about case study of the value that you get out of architectural documentation. So when we start looking at documentation, what's sometimes called the technical reader principle needs to be applied. You write the documentation for the person who's going to be reading it. And if nobody's going to be reading it, then you don't need to document it. And so you have to make a judgment, a professional judgment about the value that is going to be added by any piece of documentation. If you are doubtful about the value of documentation, then it is probably best if you don't bother capturing that particular entity in hard copy, whatever it is. The third principle, customer collaboration over contract negotiation. That one actually leads to a pretty significant culture clash. Because the basic idea here is that developers should work with the customer to solve the customer's problem. I assume that that sounds good to all of you. It certainly sounds good to me. The problem that you run into when it comes to governments and large organizations as customers is that they have a lot of history with suppliers who, shall we say, take advantage of the contract. And so if you want to make sure that things are done in an acceptable way, you've got to nail everything down in lawyerese in a contract. And that is not a collaborative kind of environment. In fact, that's an adversarial kind of environment. The entire system, legal system, is based upon adversaries fighting one another. So if you're working on a government contract, you've got this enormously detailed contract, and if you want to change the requirements, you've got to go through and get the lawyers involved and negotiate a change to the contract and all of the follow-on effects to that in terms of schedules and budgets and things of that nature. It is not a collaborative effort. It is an adversarial relationship. And what the Agile guys were basically saying is, we don't like that kind of adversarial relationship in building a product. We would much rather collaborate with our customer to build a product that solves their problem. And philosophically, I agree with that. But if you are working for, if you're a defense contractor working with the DoD, if you're working on a contract for the government, if you're working on a contract for a big multinational company that has a big entrenched bureaucracy, that's a big culture clash that you're talking about. I wrote a paper back in 2002 where I talked about the challenges that the DoD was going to have in moving to agile methods. I said that some centers are going to be able to make this change pretty readily, and other centers are going to struggle with it because it is a major culture clash for them. This is not the way that we do things here. And so, no, that one can be challenging. I agree with a lot of the thought that goes behind this, but it is difficult. And the fourth value here has a similar kind of a problem: responding to change over following a plan. There's an old saying that you plan the work and you work the plan. If you've got a lot of requirements volatility, and agile projects frequently have a lot of requirements volatility, then you have to change what you're doing. You have to change your plan to track what is needed by the project. Now, one of the interesting questions is, what impact does that have on the architecture? If architecture is the critical early design decisions, and we have made these decisions, and then something comes along that is going to make us change these architectural decisions. And if architectural decisions are non-local changes that span huge amounts of the system, isn't that putting us between a rock and a hard place? Well, yes, it is. What we try to do is we try to build architectures that have characteristics of high cohesion and low coupling and things like that, the good design principles that I'm sure you're all familiar with, so that they're relatively easy to change, while at the same time recognizing that if you have to change a major architectural decision, that may lead to a significant amount of work that's going to be involved in dealing with that level of change. So when we start talking about architecture, as far as the agile guys are concerned, yes, agile teams may be self-organizing, but if you're going to come up with a good architecture, you've got to have the skill, the experience, and the knowledge necessary to design the architecture. This is not something that inexperienced people should do. Now, if you go back and read the literature from the early days of Agile, one of the things that they talk about a lot is that people who are on Agile teams should be very experienced software professionals. You should have very few novices, if any, on an Agile team. The Agile methods are not designed for amateurs. They are designed for experienced professionals. And you may have a novice or two on an Agile team, but the expectation is going to be that the Agile team is composed of a bunch of really experienced, really knowledgeable professionals. And those are the kinds of people who know about architectures and know how to make those critical early design decisions, know what kind of changes are likely to occur, and take those things into consideration when they're designing the architecture. And when things do change, they have the skills and the knowledge necessary to deal with the changes that are occurring. And that's a little bit contradictory to the idea of doing a lot of early releases of the software where you're focusing on customer added value. You've actually got to balance, there's actually 3 criteria that we use in prioritizing the user stories, the requirements for an Agile team. One of them is customer value. And so when we talk about the priorities that an agile team faces. The big emphasis that is front and center is that we're continually adding customer value in every iteration. So we certainly are going to focus on customer value. We're also going to focus on the things that are high risk that might blow the project out of the water if we defer them too long. And so, and frequently high risk is correlated with high value. And so we're going to focus on customer value. We're going to focus on high risk. And we're also going to address in a very prioritized way, architecture spanning aspects of the system so that we basically are building a walking skeleton of the architecture. And so the challenge is to blend the agile approach and architecture together. This particular chart I took from Ken Schwaber. Ken is one of the people who invented the Scrum Agile method. He was one of the signatories to the Agile Manifesto. He was in the Snowbird meeting. I took my Scrum Master training under Ken. I stole this chart from his Scrum Master training. And what Ken said when I took my training was that in the first few sprints, typically maybe the first 3 sprints, which is what the Scrum guys call an iteration. What we are going to do is we're going to focus on architecture and infrastructure issues over the business value requirements. And as we put the architecture and infrastructure in place, we're going to shift until we are focusing after that, roughly 3rd iteration on the business value cases. But we're going to continue to spend time throughout the project, 10-20% of our time in every iteration, dealing with architecture and infrastructure issues. So yes, we do take time in the early iterations to think about the architecture issues. And we continue to think about architectural issues throughout the life of the project. So there's a balance, there's a trade-off that we have to make there. Now, in general, when the Agile guys are talking about Agile methods, they really emphasize focusing on the business value. But, when you start looking a little bit deeper into it, this need to deal with architectural issues earlier is acknowledged. I mentioned the technical documentation principle. We write for the reader. If nobody's going to read the documentation, then you don't need any documentation. In the Agile world, they sometimes talk about YAGNI. You ain't going to need it. And so the friction that we run into when it comes to architecture is we've got to evaluate the we've got to come up with the architecture, we've got to evaluate the architecture, we've got to document the architecture. Who's going to read this? If we document this, who's going to read it? Who's going to use it? In the book, Documenting Software Architectures, the architectural view is considered the fundamental unit of design documentation. And we only produce an architectural view, we only create that documentation if it addresses substantial concerns of important stakeholders. And so how do we go about prioritizing, creating documentation in a way that will address the needs of the different stakeholders when they need it? And sometimes you need some forms of documentation early, sometimes you don't. Sometimes you don't need them at all. Now, Grady Booch is well known in the architecture world. He's well known in the object-oriented design world. He is one of the 3 amigos who created UML. It was Grady Booch, Jim Rumbaugh, and Ivor Jacobson who created UML. And he has some guidelines for agile architecture, and he says all good software architectures are agile. Your architecture needs to be resilient and loosely coupled. It follows well-reasoned design decisions, i.e. it does the high cohesion, low coupling kind of thing. It is something that can be modified. You can refactor your architecture to evolve it as time goes by. Your agile process should allow the architecture to incrementally grow as time goes by. And the way that you do that is by decomposing the system into pieces where you pay attention to separation of concerns and making things nearly independent. That's high cohesion and low coupling right there, by the way, another way of saying that. Grady also says something that is not quite as obvious to me, which is that the architecture should be visible and self-evident in the code. I'm not sure that I agree with Grady on that, and I'll be the first to say that Grady is smarter than I am, much more knowledgeable about architecture than I am. But architecture is a more abstract thing than code. We want to try and make our functions and our classes visibly part of the design patterns and the architecture that we are using. And there are conventions that we can use in terms of naming classes and naming functions and things like that, that we can adopt to try and create self-documenting code that makes at least some of our architectural decisions reasonably evident. But we really are talking about something when we talk about architecture that is at a significantly higher level of abstraction than the code. And pulling the architecture out of the code may be beyond our ability. There's just too many cross-cutting concerns, too many things that are, the whole is greater than the sum of the parts kind of issues. Now, one of the things that I do like about this is this term socialize the architecture. And how I interpret that is the team needs to understand the architecture. The team needs to internalize the architecture, because the architecture should be the framework within which all of the other design decisions for the system are made. So when the developers are writing the code, they are doing that in a context of an architectural framework that everybody should share an understanding of, and we should be consistent with it and aligned with the objectives of the architecture, and I certainly do agree with that. Some advice that you can take for what it's worth. If you're building a large system, a complex system that has stable and well understood requirements, that's the kind of system that we typically would say use the waterfallish kind of a life cycle on. Now, I don't like the waterfall. I would actually use an incremental life cycle. Incremental life cycles are kind of halfway between iterative and waterfall. You have in an incremental life cycle, you are building big chunks of functionality. So an increment may be 6 months long or something like that, but you're not going to have a 3-year long increment in an incremental life cycle. There you've gone back to really to a waterfall kind of approach. And so I would build a large and complex system in terms of a number of increments. And you can, in that environment, you can do a lot of architectural work up front, which leverages what we know about architecture as critical early design decisions, things like that. If you are doing a system that has vague and unstable requirements, then the best thing you can probably do is to come up with a candidate architecture that you can then use as the departure point as you continue to evolve the system. Alistair Coburn talks about creating a walking skeleton of the architecture and then doing incremental re-architecting throughout the life of the project. Alistair is one of the agile methodologists. His methodology is called, his agile method is called Crystal Clear. And that's what he espouses. This is very similar to what Ken Schwaber is talking about with his slide on architecture and infrastructure. If you're dealing on a small project with vague requirements, at least try to get agreement on what the central design patterns, the central architectural patterns are. And hopefully that will act as a reasonable foundation for ongoing work. Now, when it comes to documenting the architecture itself, I like something that Philippe Crutzen said. He said, if it's not written down, it does not exist. Something that I have said, I have two principles that I tend to use in life. One of them is if you don't have it in writing, I didn't make a commitment. And that's because I forget things, so if you want to make sure that I'm going to do something, your best shot is to make sure that I send me an email or something so that I've got a documented thing about it. And hopefully that will get me to do whatever it is that I said I was going to do. My other principle is a lack of planning on your part does not constitute a crisis on my part. But anyway, you want the architecture to be documented sufficiently so that it supports the different stakeholders doing their jobs. And that goes back to the technical documentation principle that we talked about earlier, which is you write for the reader. So who are the stakeholders that are going to be using this documentation? How are they going to be using it? How is it going to add value to them? If you're not sure, then probably you shouldn't document it. If you decide that you need that documentation, then you can probably go back and create it. But if you create it and you did not need it, then you just wasted that particular effort. Why do we use documentation, design documentation of any kind, but really architectural documentation? Well, one way is to educate new people on the team about the system. And that is arguably the most important reason for documenting the architecture is so that new developers who are being brought onto the team can have a roadmap of how the system hangs together that will bring them up to speed more quickly on what the system is doing. I personally consider the idea of documentation as a vehicle for communicating amongst the stakeholders as being a secondary issue. Now, it is certainly true that when you document the architecture, that provides a record for people to refer back to in the future, including the architect. The problem that I have with that is that when we're talking about architectural documentation, the thing that I want to know is not the thing that you capture in the graphical diagrams that we have been talking about to this point in time. When we talk about that, the UML diagrams, the SOA diagrams, things like that. That's not the kind of documentation that I really want to have in the future. What I want to have in the future is the design rationale. You remember back, we had a chart back towards the beginning of this discussion where we talked about documentation. The presentation, the graphics, and there was some stuff about various and sundry pieces, and one of them was the rationale. The thing that I would like to have in the future as an architect is, why did I make that design decision? What was the rationale? What was the reason that I made that decision? Because we forget. And so you decided to go down this particular path. Did you have a good reason for going down that particular path? 3, 4, 5 years from now, I'm looking back at a design decision and I'm saying, why in the world did we do that? That was really dumb. Why do we want to do that? Well, it may be that there was a good reason for going down that particular path. And I've forgotten what that reason was. Have any of you ever had the experience of going back and changing a program that you wrote months or maybe even years earlier, and you're halfway through making a change and you suddenly realize, oh, that's why I did it that way? And then you just say, I have to back everything out that you've been working on. I've had that experience. I forgot why I made a particular design decision the way that I did. And I thought I could change something, to make things work better for some reason or another. And I started to make the change, and it turned out there was actually a reason I did it that way to begin with, but I forgot. The other possibility, or another possibility, is I made that design decision for a good reason that was true at that time, but things have changed since then. So a design decision that was appropriate at a given point in time with a given set of business constraints, a given set of technologies, as time goes by, those constraints, those drivers may have shifted. And so when I'm looking back, I may say, oh, that's why I did it then, but things are different now. So if I want to change that decision now, I could legitimately do that. And then I've got to look at the consequence of change. How much is it going to cost to make this change? How much value am I going to get out of it? And I can make an informed decision at that point in time. There's actually another reason for making a particular design decision, which is I had 7 possibilities and I flipped a coin to decide which one to pick because I had no reason to think any of them were superior to any of the others at that point in time. Or maybe I culled it from 7 down to 3 and I said, okay, which one, any of these 3 will do. And so write that down so that if at some point in the future something has changed, so that you say, oh, this other way would have been far better. And you know why, maybe it was one of the 3 and, it just happened to be one of the 2 that a path that you did not go down. Now now you remember, now you're prompted to remember that. As far as documentation as the basis for systems analysis and construction, yes, there is some value to that. In particular, if you're using tools like AADL, which allow you to do, that's a tool for doing an architecture description language that can help you to model and analyze and simulate the architecture of the system. If you're using a tool like that, it's very powerful. If you're drawing your architecture on a whiteboard, once you get down to the point of writing the code, you could erase the whiteboard. Now, you would still have those other 2 reasons for keeping that documentation around. And you might decide to take a digital photo with your phone of the whiteboard before you erased it so that you could capture some of that information. That's not perhaps the most effective way of archiving that particular kind of design documentation. Now, when it comes to the notations that you are going to use for your architecture, when you're documenting your architecture, you can use an informal notation. You can use any kind of, you could use PowerPoint or Visio or, any other kind of graphic tool that will draw arbitrary boxes and lines for you and roll your own notation. You're better off arguably to use what's called a semi-formal notation, something like UML, which has a standardized set of elements and a standardized set of connections and standardized rules of construction. And that tends to be preferable to the informal notations, because there's a basis for continuing to interpret them consistently as time goes by. You can go as far as a formal notation that is mathematically based. For the architectures, those are generally referred to as architecture description languages. When I mentioned AADL, the architecture analysis and design language is a formal notation. You can do all kinds of formal methods, kinds of stuff using AADL. Those kinds of formal notations are not widely used. AADL was designed for building embedded real-time systems. Building real-time systems, embedded real-time systems, is really, really hard. So using tools like AADL to help you design and build a system that meets its non-functional requirements is arguably an investment that is worthwhile, but it is a significant investment. I'm going to take a 10-minute break at this time. We're a little bit more than halfway through. So you guys can go get a drink of water or something. No, and we'll resume this discussion in 10 minutes. Okay, let's resume with our discussion. We were talking about views a little bit earlier. One of the kinds of views that we mentioned was module views. Module view captures a static view of the structure of the system. A module is an implementation unit, typically a class, could be a package. Relationships that modules have to one another are one module is part of another module, one module depends on a module, one module is a module. So what would we mean when we say that one module is part of another module? Well, that would be aggregation, right? So if one module is part of another module, that would be some form of aggregation or composition. Depends on is a little bit more of a message passing kind of relationship. Is basically inheritance. Okay, so if you were doing a class diagram, if you have an association between two classes, that's representing some kind of depends on relationship. If you're doing aggregation, that would be one module, one class is part of another class. And if you're doing inheritance, then you'd be saying that one class is a subclass of another superclass. You're usually going to have at least one module view of any system that you are building. We talked about component and connector views earlier. So component and connector views are going to be more dynamic views. They're going to emphasize the elements that are around at runtime, things like objects. If you're doing object-oriented design, objects are instances of classes. So when you're doing a class diagram, then you draw what's basically a picture of the classes, of the templates that are being used for the different entities that make up a system. And then when you create instances of those classes at runtime, you would use those for sequence diagrams and activity diagrams and communication diagrams and things like that. And you can include interfaces to servers and data stores and things of that nature. So the component and connector view, the connections would be the pathways that where we have interactions. In component and connector views, we can talk about ports, which are interfaces between components. Connectors have interfaces, which are roles that to play about how connectors can be used by the components to interact together with one another. And the third category was the allocation view. So we can map software units to other elements of the environment, such as the people who are going to be assigned the responsibilities for doing the work, or the processors that a set of processes is going to be residing on, things of that nature. Usually with allocation views, we're going to be looking at the properties required by the element and the properties provided by the environment. If you're talking about a work breakdown structure kind of a view, the properties required by the element are, the amount of time that's required to do it, and the properties required by the environmental elements are the people who are going to be applying that time to build that particular element. Saying that architectures are abstractions is a pretty obvious statement. This statement right here, and this comes from the Software Architecture and Practice book, you can't see the architecture and the low-level implementation details. That was the exact problem that I had with Grady Booch's comment that the architecture should be self-evident in the code. You really can't see the architecture in the code. You can kind of see part of it. You can build tools or use tools that will aggregate a lot of the low-level details to create higher-level abstractions, but they are not perfect. Re-engineering your architecture is a difficult thing to do, even with tool support. It tends to be what we would call a semi-manual process. There's part of it that can be automated, but there's a big part of it that requires human intervention to close the loop. There are workbenches, which are frameworks basically for helping you to reverse engineer designs and architectures out there, but they are a little bit limited. UML is, as was said before, popular modeling language. UML version 2, technically speaking, was it 2.1.5 is the current version, is a standard that's maintained by the object management group. Frequently, we use UML as the notation for capturing our designs, including the architecture. Here is the set of 14 different diagrams that I talked about. They are categorized as structure and behavior diagrams. There are 7 structure diagrams. At the architectural level, we usually talk about package diagrams, although we can also certainly talk about any of the others, including class diagrams. For the behavioral diagrams, interaction overview diagrams are logically the equivalent of a package diagram. A package diagram is composed of other packages and other kinds of structure diagrams. So it is a higher level abstraction than a class diagram. Similarly, an interaction overview diagram is composed of other interaction overview diagrams and other kinds of interaction diagrams, such as sequence diagrams. And so it is a higher level abstraction also. I mentioned the term UML as sketch. One of the things that we tend to emphasize in modern day design is having the team stand around a whiteboard and collaborate together and coming up with the design. When we're doing UML as sketch, we're typically focusing upon the hard parts of the problem. So the designs that we're coming up with may be informal, certainly will be incomplete. In the agile methods, this is what we tend to focus on, is this UML sketch kind of approach. Now, as I mentioned earlier, if you're in an agile kind of context, most usually the expectation is that you will design on the whiteboard and then erase the whiteboard once you've written the code. Now, you can also do UML as blueprint or UML as programming language. UML as blueprint, you can do 2 different things there. One is that you can do code generation from your design diagram. And so you build your UML design in a tool, and then you can generate a skeleton of your program from that blueprint. And then you have to fill in the skeleton that you have completed. So code generation from UML as blueprint is certainly going to be incomplete. The other thing that you can do is that you can look at the code and you can reverse engineer the UML diagrams from the code. And in fact, that is the most common usage of UML tools, is to reverse engineer UML diagrams. Now, back in the 1960s, 1970s, a popular design notation was flowcharts. And students used to be told, flowchart your program before you write the code. And programs were written that would look at your code and would generate a flowchart from it. And that was basically a way of sidestepping the design process altogether, which is not entirely a good idea. The flowcharts were not very good that were generated using that particular approach. Basically, as every line of code had a box drawn around it and then arrows between the boxes. That's not necessarily the case when you're reverse engineering UML diagrams from the code. In particular, if you've got a tool that can generate interaction diagrams such as sequence diagrams, which not all of the tools do. Reverse engineering a class diagram is pretty straightforward from most programming languages. Reverse engineering a sequence diagram requires a little bit more in-depth analysis. But the advantage of that is that if you're doing UML as sketch, and then you're writing the code and you erase the whiteboard and you decide that you need your UML design, you can use the tool to generate a complete set of UML diagrams from your code. And so That makes the design and coding process an iterative process with nice, clean UML diagrams being generated from your tool based upon the latest version of the code so that your design diagrams are in sync with what the code is actually doing. And so that's a desirable thing. This third category of things down here, where you're using UML as a programming language, it is possible to specify the bodies of methods in your UML diagram using a method stereotype in a note in your UML diagram. And then your tool can go off and automatically do code generation. And it's more than just a skeleton. You've actually got the body of the methods embedded in the UML as notes, basically. I'm not entirely enthused about that, but it may turn out that that's the greatest way of writing code ever. I guess we'll all just have to wait and see. That's not something that seems to be done a lot right now, but it may be the wave of the future. Who knows? Now, when we start looking at using UML, one of the kinds of UML diagrams is a use case. So that's actually a behavioral diagram. Larman has a couple of case studies in his book. One of them is simulating the game of Monopoly. Now, this is not playing Monopoly with the computer. This is simulating the game of Monopoly. So what the external actor, who is the observer in this particular case, is doing is he is basically saying, simulate the game of Monopoly with, say, 5 players. And the computer goes off and simulates the game of Monopoly and tells the observer what the rolls of the dice were and how the pieces were being moved around the board and things like that. Now, use cases are a popular way for describing requirements. They are very good at describing systems where there is significant interaction between the user and the system. In a lot of science and engineering systems, including this one right here, which is a simulation of a real world kind of a system, use cases aren't really a good way for capturing the requirements for the Monopoly game. The rules for Monopoly are actually the articulation of the requirements for the Monopoly game. But anyway, if you were going to model that, the first thing that you would do, and this is an object-oriented design thing, is that you would create a domain model for what Monopoly is all about. So you go through and you look at the application domain, and you say, I'm looking at the rules for Monopoly, and these are the first set of things that I see as being critical things here. The Monopoly game, the players, the pieces, the die, the board, the squares. And if you were doing this, Larman does this using the UML as sketch approach. So all of these diagrams are hand drawn. In his other case study, which is of an automated cash register, his diagrams are tool drawn. The question becomes, if you've got this diagram that you've drawn on the whiteboard, should you put it into a tool and draw a nice tool drawn kind of UML diagram? And the question then becomes, who is going to maintain the UML design document that you're creating here? What are they going to use it for? So that goes back again to that technical documentation principle. Who's going to read your design? Who's going to be using it? And then you go through the exercise of creating your domain model by adding in attributes that describe the different objects that you see in the application domain. So a die has a face value, players and pieces have names. Pieces have names like the top hat and the race car. There's 40 squares in Monopoly on the Monopoly board. And you describe the associations between the different elements. So the Monopoly game is played with 2 die. You play Monopoly on a board which contains 40 squares. The players who play Monopoly on pieces, there's a 1-to-1 relationship between players and pieces. the pieces are on squares on the Monopoly board. So this is what's called a domain model. It describes the domain in terms of objects in the application domain. And then we can refine this in terms of a design model later. Now, one of the things that we typically do when we're doing object-oriented design is that we create both static and dynamic models. And usually we will move back and forth between those. You will see things when you are modeling the interaction of different objects in the system that you are modeling, and that will feed back into identifying methods, which are operations in your class diagram. Now, the diagram on the left of this particular picture is not a domain model. It's actually a design class diagram. It's for a dice game in this particular case. The Monopoly game is a different example. But when we're playing dice, we roll die. In this case, we'll roll 2 different dice, so we would actually have 2 different rolls going on there. But anyway, you typically move back and forth between the static and dynamic models, revising each one of them in an iterative way. So here is the system sequence diagram. The system sequence diagram treats the external actors and the system as a black box. So in this particular case, the only external actor is the actor who is called the observer. I might have called it the user or the operator. And in this particular case, we're going to have the external actor initialize the system with some number of players, between 2 and 8. And then play the game, and then the system is going to execute a loop as long as there is not a winner of the game of Monopoly, telling the observer what the rolls of the die were, and having the players move their pieces around the different squares on the board. Now, I mentioned earlier that when it comes to documenting architecture, what value are you going to get out of that? There's an interesting case study that Rick Kasman and some of his colleagues did a few years ago. They looked at an open source software product that was a reasonably good sized one, about 200,000 lines of code. There was not much design documentation available for this. And what Rick's team did was they reverse engineered the architecture from the code, which took 2 to 3 person weeks of effort. And then they said, here's the architectural documentation. And do you find this useful to you? How would you use this architectural documentation? Now, I'm going to say that in my opinion, the architecture of this open source product is not very good. I'm going to let you take a look at some of the documentation that was drawn, and you can draw your own conclusions. These are some of the module relationships. This was HDFS, that's the Hadoop file system right there. And you can see a bunch of nodes. In there with an awful lot of connections between them, isn't there? Low coupling to me. That looks like there's a lot of coupling that's going on there. So I don't think of this as being a very good design. Here's another picture that comes out of that, the module relationships here. Again, you see a lot of coupling going on in this particular system. Now, my observations there are just, my personal value judgments. You may agree or disagree. But the point of the experiment that Rick and his colleagues were doing, there were 2 categories of people that they were interacting with on this open source project. There were committers and outsiders. Committers were the people who were the experienced contributors to the Hadoop file system. And they basically said, we do not need or value this architectural documentation. We're keeping all of these architectural details in our heads. 200 lines of code is not a huge system. You can actually argue that that's small enough so that an experienced professional can keep the architectural details in their head. The outsiders, however, said, we're getting value out of this because we are able to use this architectural documentation to educate ourselves about the system. And so we move from being outsiders to being committers more easily. Another thing that occurred was some decentralization. So when people had a question about the architecture, instead of going to a committer and asking, what's the system doing in this particular case, they looked at the documentation. And so that was a decentralization that occurred. So the bottom line was that the committers were not willing to maintain the architectural documentation that Rick and his team came up with. And so you could legitimately ask yourself, was this just a wasted effort? Well, the conclusion that Rick came to and his colleagues came to was that we need better tools for helping us to automatically reverse engineer the architecture from the code so that the committers have to spend very little or no time in order to maintain architectural level documentation. And as a researcher, that's a perfectly reasonable conclusion to reach. There was value from the architectural documentation that supported one of the reasons that we want to document architectures, which is to educate developers about the architecture. Could the committers have gotten value in terms of things that might happen in the future if they had kept that architectural documentation around? Don't know that. Experiment did not last long enough for us to be able to really meaningfully ask that particular question. So when we want to figure out what the architecturally significant requirements are, what you may observe is that a lot of the stuff that we see in the requirement specification are functional requirements that don't really affect the architecture that much. A lot of times you've got to extract the architecturally significant requirements from business goals from the organization as a whole, or excavate them by implication from the requirements documents. So when we're looking at the different kinds of design decisions that we have to consider, when you're thinking about allocation of responsibilities, what we would look for are requirements that deal with things about, when we're talking about responsibility, we're talking about who's responsible for knowing something, who's responsible for doing something in the system. So that's object-oriented design. Who's going to be responsible? What are the different user roles in terms of the external actors of the system? What are the different modes of operation for the system? What commercial packages may be integrated into the system? So a number of these things deal with external actors from the original system. What's the coordination model? How are we going to coordinate between the different threads within the system, different elements, sensors, actuators, and things like that? What are the requirements that address those kinds of issues? The data model. Are we doing some kind of NoSQL database that meets the CAP properties? Are we doing a relational database where we want to meet the ACID properties? What are the information flows that are needed between the different components of the system? What do we need to be concerned with in terms of access rights and security kinds of issues? How can we expect the data itself to evolve as time goes by? What resources do we need to manage for the system? Time, concurrency, memory. Those are all things that we might need to manage. And in particular, we might need to scale. So you might start off with 100 users and go to 100,000 users. Can you support scalability? Do you have requirements that may deal with the continuing scalability of the system? We may have to deal with mapping between the architectural elements in terms of the evolution of processors and network configurations and things like that. Do we need to think about binding time decisions? What requirements do we have dealing with things like regional distinctions? internationalization is a big thing these days. So you build a system that's targeted towards English language users, and then you decide you want to sell it in Germany. So now you have to do all of your prompts and everything in German. Did you design the system so that it was easy to swap out the German language interaction stuff with the English language version of things? And then, of course, we have picked particular technologies. How are the technologies going to change, or how might we expect them to change as time goes by? We've got all of these categories of things that we need to consider when we're looking at potentially important architecturally significant requirements. Fortunately or unfortunately, I'm not sure which, you really got to talk to people to understand all of these different issues. Now, we as experienced architects may have some pretty good ideas about what quality attributes are going to be important for this system, because we have worked with similar kinds of systems in the past. But the stakeholders themselves may not have any really good idea of what the system is capable of doing, or what they want, or what they need. And so one of our jobs as good professionals is to interact with the different stakeholders and solicit the information from them about what the important architecturally significant requirements are in their environment, whether the driver is going to be. We need to put together some scenarios for how the system can be used, and then have the stakeholders, we need to have the customer involved with prioritizing how we're going to deal with the different quality attributes in this particular system. So we know that things like performance and security are going to conflict with one another. How are we going to resolve that? Well, the people who make those trade-off decisions in terms of their priorities are the stakeholders, and they may have conflicting requirements. And so we need to have a way of integrating their different values and judgments in order to come up with a system that will meet everybody's needs to a reasonable degree. One of the techniques that we can use for doing all of this stuff is something called a quality attribute workshop. So what we do in a quality attribute workshop is that we get together with the different stakeholders and we have a presentation about what the system that we are building is going to do. We talk about the mission, we talk about the architectural plan that we have. We say, what are the architectural drivers? And you've got to give the stakeholders who are participating in this workshop some idea of what the categories are. And then you do some brainstorming of the different scenarios for how we might use this system and how that might be impacted or impact the different quality attributes. And then we need to consolidate those down into a coherent and consistent set of expressions of the scenarios. Brainstorming, you wind up all over the map. And then you've got to prioritize the scenarios, which ones are more important than others. And different people will have different agendas and different priorities. And so you've got to figure out how we're going to do things. Usually some form of multi-voting is a good technique for resolving the different priorities that different stakeholders have. And then you look at the highest priority scenarios and you start refining those in more detail. So we got to understand the business goals for why we're building this system, because that drives the requirements that we are concerned about from an architectural perspective, which may or may not be actively captured in the requirement specification. A lot of times business goals will result in coming up with quality attributes. And in fact, they may affect the architecture without generating a quality attribute requirement at all. They may generate constraints on the system, which will limit what some of your design choices are without ever actually becoming a quality attribute themselves. So for example, you may have a business goal that says, use a relational database. I still remember decades ago talking to somebody, and he said, we need a relational database for this system. And I said, no, we don't really need a relational database. This is not that complicated a system. We can just do this with flat files. Don't need anything as sophisticated as a relational database. No, I want a relational database. Well, from a technical perspective, we don't really need a relational database on this. Now, relational databases at that point in time were pretty expensive things. And we need a database because I've got a database group and I need to give those people work. Oh, I understand. You need a relational database. That was a business goal. It was one that was never written down. It was a political kind of a thing. It certainly wasn't a quality attribute. It was a non-functional requirement. Absolutely. It was a constraint, but it wasn't really a quality attribute, but it certainly affected the architecture for the system. Now, PALM is the pedigreed attribute elicitation method, and this is another workshop. Now, notice we had a quality attribute workshop. We're not about to have a pedigreed attribute elicitation method workshop. This is figuring out what the business goals actually are. Now, you may find this difficult to believe, but there are lots of organizations out in the world that have never really articulated what their business goals were or what the business goals for a particular project were. So what are the business drivers? What are the architecture drivers? What are the business goals that these things should be aligned with? What quality attributes can we derive from these business goals that we're eliciting here? What is the source of these business goals? Pedigreed. The term pedigreed says there is a source, a pedigree for this particular business goal. What is the source? Is it some pet peeve of the CEO or the CIO, in which case we're going to salute and say, yes, sir, and go off and address it, whatever it is. But if the CEO or the CIO changes, then that particular business goal may warp or vanish altogether. And you would like to know where the quality attribute drivers came from, so that you don't get caught betwixt the gears when things like that happen. We're going to generate a utility tree. Now, utility tree is basically used to help us measure the value for the different quality attributes that we want to achieve. Now, measuring value would frequently or usually like to do that in terms of money, because that's what managers care about is money. Problem is, a lot of times it is hard to measure things in dollar terms. So a thing that the economists have come up with a number of years ago is basically utility. And so what we do is we say, we will let you assign a utility value to each one of these things that we care about. And presumably there is eventually a mapping to money that's going to occur here, but it's unclear what that relationship is necessarily going to be. And so what we're going to do is we're going to look at each one of the quality attributes and the architecturally significant requirements that we've identified in our scenarios. And we're going to look at the value of that requirement, the business value. And then we're going to look at the architectural impact, and we're going to do a cost benefit analysis where we're measuring cost and benefit in terms of utils or utility that we can look at. So in an ideal world, you would have a set of architecturally significant requirements that were clearly identified, and you could just go from those. But in the real world, frequently, you don't even know what the business goals are. So you may need to go through one of those PALM exercises to figure out what the business goals are. If there are stakeholders who are critical and their concerns have not been addressed, you may need to do a quality attribute workshop to make sure that the quality attributes of these stakeholders have been expressed and are being considered when we come up with the architecture for this system. And then we need to prioritize our architecturally significant requirements, and we can do that. Use a utility tree to help us do that. So we've got to figure out what our architecturally significant requirements are, and we've got to look at the design decisions we're going to make in achieving those. Then we're going to have to make trade-off decisions and relating all those things and pull it all together. Now, there is actually a process called cost-benefit analysis that you can use for going through this. This is actually described in the Software Architecture in Practice book. I did not choose to put it in this particular overview presentation. Just be aware that these kinds of decisions are the kinds of things that you need to do in order to come up with an architecture that meets the needs of all of the stakeholders for your system. And so this kind of gives you the skeletal foundation for that particular discussion without really going into the detail about how you would go about doing that. Then we can do, we've got the quality attributes, and so we can basically do an attribute-driven design. We know what the requirements are. We know that the requirements are going to change, but we can start designing as soon as we have a minimum viable set of architecturally significant requirements that can act as the foundation for the design. Well, how do we go about doing our design strategy? You fundamentally got two different approaches, breadth first versus depth first. In general, you would prefer a breadth first kind of approach. But there are some things that may affect that strategy. One is that key personnel may be available for a limited amount of time. So maybe your database experts are only available for a certain amount of time. So you're going to have to go depth first into the pieces of the system that are going to be centered around database issues, whenever those experts are available. Similarly, for risk mitigation, if there are high-risk pieces of the system, then you're maybe going to want to focus on those and analyze those in enough detail so that you understand those issues well, before you commit yourself too deeply into the system. So in general, you would like to do breadth first because that allows you to manage the allocation of the work to the teams and people, and it allows you to think about interaction of items at the same level. If everything else is equal, then you're going to probably prefer a breadth first kind of strategy for going through the design exercise. But realize that we may want to do depth first on at least some pieces of the system for good reasons. And so when you start looking at how design works in general, this is very common. In fact, this is one of the reasons that design is frequently referred to as an opportunistic process. Opportunistic in the sense that sometimes we have to take advantage of the opportunity to pursue some issues in more detail because of constraints that exist in the outside environment. And so then we look at the patterns and the tactics and the design checklist that we have. Usually there will be some architectural pattern that you will use as a basis for your candidate design, and then you will augment that with different tactics for addressing different quality attributes that you care about. Then you will look at your design checklist to look at how well you're addressing the different things that you care about. If you are building a system that is reasonably similar to other systems that you have built in the past, then likely you will be making design decisions in terms of patterns and tactics and things like that will hit several different architecturally significant requirements at the same time. But as you're going through your design process, you may look at it and you may say, we have not addressed all of the architecturally significant requirements in this design. Well, why have we not satisfied all of the architecturally significant requirements? We may have a quality attribute that's been allocated to some element that we now need to decompose into more parts as part of the ongoing design work. It may be that one of our architecturally significant requirements is actually a functional responsibility. We may have constraints on a parent element. And so now we have to think about how we're going to deal with this failure to satisfy an architecturally significant requirement. One of the things you can do is you can backtrack. You can reconsider the design altogether. But maybe you don't want to do that. Maybe you say, okay, we need to continue going down the path. And so you may delegate a requirement, whether it's a functional requirement or a quality attribute requirement. You may delegate it to one of the children of the design tree that you're looking at right now. You may distribute it amongst different children of the design tree. And so we were talking about the parent elements on the previous slide. So we're continuing to move down our design tree in a breadth first kind of a way. Have we met this requirement? Have we addressed this requirement yet? And you may look at it and say, oh, our current design, we cannot meet some of our architecturally significant requirements. We'll just come to an impasse. In which case you've got to backtrack and go back up your design tree and redesign, or you can push back on the requirement. You can go to the stakeholders, to the customer, and you can say, oh, you've got this requirement to do this thing in 1/10 of a second. Well, that's going to cost us $5 million to solve that, to meet that requirement, that performance requirement. Now, if you're willing to accept half a second time to do this, we can do that for $50,000. Frequently we have nonlinear relationships between things like performance requirements. And so your customer may say, oh yeah, I'm perfectly willing to relax that requirement, to save, a boatload of money. And periodically you ask yourself, are we done? No, at some point in time, we're doing our design and we've got to decide, are we done? Is it time to start coding? Is it time? Are we done with the design? Have we satisfied the contractual specifications that are out there in terms of what deliverables there are in terms of architectural documentation and design specifications and things like that? Have we finished our design budget? Have we run out of money for doing design work? You're doing this attribute-driven design work. Sooner or later, you got to say we've done as much as we're going to be able to do. Are we at a point where we can say good enough and forge ahead? You may want to release early versions of the architecture to some of the stakeholders because they can start using that in doing their work and get some value out of that. So, that's an ongoing negotiation that can occur. Ultimately, what we're talking about here is that the architect is working at the interface between the business and the technical side of the project. So you are in many ways an interface between the business drivers for the project as well as the design part of the project. And so you are going to be dealing with things in terms of the economic implications of the architectural decisions that you're making. And so you are doing cost benefit analysis to help you decide what is the impact of this design decision? How is that going to affect what I'm going to be doing down the road? Now, we were talking about utility a little bit earlier. And one of the things that's useful here is to consider what the utility response curve is for the different stakeholders. Now, different values of utility are going to provide different levels of satisfaction to different stakeholders. And you don't have to have absolute numbers like, this is worth $30,000. As long as we can do relative things, human beings are pretty good at comparative kinds of estimation. So we can look at utility response curves, and we can look at things like this. So in the curve in picture A up here, you've got two levels of response here. So you've got utility, which is your y-axis, and you've got a quality attribute, an architecturally significant requirement, if you will, on the x-axis, and you've got two levels in there. And you ask yourself, what's going to happen as I move the A and the B lines back and forth on this curve? Well, you've got some curves which are curved down, and in B, you see one that is curved up, and in C, you see one that's kind of an S-shaped curve, and in D, you see one which is a linear kind of a curve, and in E, you see a stair-step kind of a curve. And if you have an intuitive understanding of the shape of the utility response curve, then that gives you an idea of how sensitive changes in the quality attribute are going to be, or how sensitive the utility is going to be to changes in the quality attributes that you're looking at. And if you can draw this conceptually, you don't have to worry about the specifics too much, as long as you get an idea for where you are. So for example, when you're looking at this difference between A and B on curve C, A and B, you'll notice those lines are on the ends of the steep part of the S-shaped curve. Well, that gives you a very different response. If you've got a stair-step kind of curve like in E, you move A or B or C just a fraction, and you may move dramatically in terms of the utility that's going to be received by the different stakeholders. So what we would like to do is talk to our different stakeholders, and they have different priorities in terms of what they want to achieve, in terms of the best case and the worst case values of the different quality attributes that our stakeholders are willing to settle for or willing to pay for. And if you've got an existing system, what is the current quality level and what is the desired quality level? We can anchor these on a scale of 0 to 100 and do a cost benefit analysis. And that's as much depth as I had to get into this. I've actually finished a little bit early here. Okay, what I can actually do here, hold on just a second. And let me go over here and let's see. I've kind of waved my hand at the cost benefit analysis. I could actually go through and look at that. Let me share my screen with talk for just a few minutes about cost benefit analysis. I was waving my hands at that, but I can actually talk in a little bit more detail about that. So cost benefit analysis, we were talking about the different scenarios that we have and prioritizing those. You'll remember that discussion, and assigning utilities. Let me just talk for a few minutes about that. In fact, let me just skip ahead a little bit in this. Here's an example of actually doing this. This was a project for an Earth observing system for NASA. This comes again out of the Software Architecture and Practice book. And so here's a system. It already is in existence. So we're talking about some maintenance work on this. And there was an ATAM exercise that was done. That's an architecture trade-off analysis method. It's what ATAM stands for. And so there were a whole bunch of changes that had been identified that the stakeholders would like to see for this particular system. But the budget was limited. And they said, we can only afford to pay for a small percentage of this how can we decide which of these scenarios we should do? So here is, and this is a simplified set. Here is 10 different scenarios that were discussed. And there were things like number one is reduced data distribution failures that result in hung distribution requests during manual intervention. On down to number 10, the system should process a 50 gigabyte user request in 1 day and a 1 terabyte user request in 1 week. So here are different scenarios for changes that they might like to see in the system. So the question becomes, what's the current value for these? So we've got an existing system. And for scenario 1, 5% of the requests get hung. For system 10, 60% of the requests meet that performance goal. What would be the worst case and the best case that we could see, looking at our utility response curve? And so we've got values that are laid out for worst case and best case. And then we put in what we would like to see. So the current value is 5% hung for scenario 1. The best case would be 0% hung. What we would like to do is we'd like to get 1% hung. Now, if only 1% got hung, then we would say that that was pretty good. So you go through and you look at the different scenarios and you characterize the best case, worst case, current, and desired cases in terms of what the different stakeholders would like to see. And then you can go through and you can start prioritizing these by giving votes to the different stakeholders and letting them allocate their votes to these different scenarios. So for scenario 1, the stakeholders allocated 10 votes to that one. For scenario 2, allocated 15 votes. Now we can go through and start assigning the utility for this. Now, so I'm looking at this and I'm saying, okay, I've got 10 votes for scenario 1. What is my worst case? What is my current value? What is my desired value? My best case value? So worst case, current case, desired case, best case. How would I value each one of those things? Now, I've got a bunch of architectural strategies that I can use for addressing these different things. So one of my architectural strategies is creating order persistence on submitting an order. So what we're going to do is we're going to store an order as soon as it arrives in the system so that we don't lose it. That's going to affect scenarios 3, 5, and 8. If we implement order persistence, we expect that we will move from 5% of our orders failing in scenario 3 to 2% failing. So this is giving us our expected response for implementing this particular strategy for a given scenario. And so you go through and you'll see some of these strategies will affect multiple scenarios. Some may affect only one scenario. And so we go through and we start looking at the utility that's going to be expected there, and we can interpolate the expected utility from implementing a particular scenario in terms of how that falls between the current utility and the desired utility. And so you can see that interpolation being done. That's the utility for each one of these architectural strategies that we're looking at. And now we can go through and we can start thinking about the total benefit for each one of these strategies. So you look at each one of the different scenarios and you say, okay, for strategy number 1, we weighted scenario number 3 is having 15 votes, and scenario number 5 is having 15 votes, and scenario number 6 is having 10 votes. What is the raw architectural strategy benefit? Looking back at our utilities, we can normalize that by looking at multiplying the weight times the raw value. And so that will give us, an idea of what the benefit, the total architectural benefit is when we sum up all of those normalized architectural strategies. And so what we see in there is that we have total architectural strategies or benefits. For strategy 1, we get 950. For strategy 2, we get 200, and so forth. And so we look at those and we say, how much is it going to cost to implement each one of these? Well, there is a benefit and there is a cost. If you have a benefit and you have a cost, you can do a cost benefit analysis. we can look at the value for cost. That's what strategy VFC stands for. What is the value for cost of each one of these architectural strategies that we would like to take a look at? So 950 divided by 1200 is 0.79. 200 divided by 400 is 0.5. We can go through and look at the value for cost for each one of our things. Number one is strategy number one. Number two is strategy number three. Number three is a tie between strategies 2 and 4 and 8. So it seems pretty clear that we are going to implement strategy 1 and strategy 3. And the question then becomes, have we run out of money? We originally said that we could only pay for 10 to 20% of the things that we were looking at. Well, that is architectural strategy number one is the most expensive one. We may have run out of money after doing strategy number one. That is the highest value that we can get for the money that we have available to spend.